Picture this, an autonomous car is flying down the highway. It's streaming raw sensor data to the cloud at tens of gigabits per second, while at the same time it's scanning the road ahead in millimeter detail, through dust, thin plastic, even cardboard. Now imagine that both of those jobs, super-fast communication and high-resolution sensing, are handled by the exact same little box. That's not sci-fi anymore. A team from Huawei and Shanghai Jiao University just published a Nature Communications paper about a 220 GHz Terahertz device that does exactly this. 64 Gbps wireless plus millimeter-level imaging in a 20x10 cm package. In this video, we're going to unpack what they built, how it works, and why it could become the brain and eyes of future 6G cars and robots. Before we dive into the hardware, let's quickly answer a core question. What even is terahertz? On the spectrum, terahertz frequencies sit between microwaves and infrared light, roughly 0.1 to 10 THz. Today's 5G wave systems live down in the tens of GHz. This device operates around 220 GHz, right in the lower terahertz band. Why does that matter? Higher frequency means more bandwidth, so you can send a lot more data. Shorter wavelength means you can achieve millimeter scale resolution when you use those waves for imaging. And terahertz waves can often penetrate dry, non-metallic materials, like cardboard, plastics, or fabric, without the ionizing effects of X-rays. So THz is attractive for both communications and non-destructive sensing. The problem is, until now, we mostly built systems that did one or the other. Let's talk about the device itself. The researchers built a portable 220 GHz band prototype using high-temperature co-fired ceramic system-in-package technology, HTC-ISAC. If you're not familiar with that, it's basically a way to stack multiple RF components in a compact, robust ceramic package with low-loss interconnects. Inside a 20x10 cm box, they integrated an 8-element transmit phased array, a 4-element receive phased array, frequency multipliers, mixers, LNAs, and power amplifiers, a parabolic reflector antenna, and an FPGA-based baseband that handles OFDM beam steering and sensing algorithms. In communications mode, the device operates around 220 GHz, achieves 64 Gbps data rate, works over roughly 38 meters, supports plus to 30 degrees of beam steering. Crucially, the same RF front end and the same OFDM waveform are reused for sensing. This is what we mean by integrated sensing and communication. Not two separate boxes bolted together, but one shared platform doing both jobs. So how does this thing actually maintain a 64 Gbps link to a moving receiver? First, the beams. Because it's a phased array, it can electronically steer a narrow terahertz beam instead of broadcasting in all directions. That concentrated beam boosts link budget and helps fight path loss at 220 GHz. In the experiments, the transmitter acted as a base station and the receiver was mounted on a moving platform. The device could steer across plus to 30 degrees, and the receiver moved at about 2 meters per second. Second, the beam tracking intelligence. They used a 2-stage algorithm stack, STARE, which stands for Spatial Time, Location Aware, Adaptive Region Guided, Enhanced K-means. It takes reflected signal data and extracts trajectory information, where the user equipment is and how it moves. It pays special attention to beam switching regions, where the system needs to hand off from one beam ID to another. Bright, Beam Region Integration, Guided Hidden State Tracking. This is built on a hidden Markov model. It assigns the user to hidden states like approaching the switching zone, inside it, leaving it, or far away. It uses a Viterbi-style algorithm to track the most likely state sequence over time, even when measurements are noisy. Together, Stare and Bright let the system keep the right beam pointed at the moving receiver and decide when to switch beams without dropping the link. On top of that, they tackle a very real hardware issue: low-precision ADCs and DACs at extremely high sampling rates. They use a multi-precision, non-uniform quantization scheme. The same signal goes through different gain paths or different quantization views. They rescale and digitally combine those views to simulate a finer effect of quantization. That trick alone helps them support QPSK with just 2-bit precision and 16 QAM with 3 bits, and it boosts throughput compared to a more naive ADC design. Now the sensing side. For the imaging experiment, they didn't switch to a new radar waveform. They kept the OFDM signal dialed back to 2 GHz of bandwidth and still ran a 10 Gbps link for communication. They mounted the front end on a robotic arm, pointed it at a sealed box that contained a metal plate with cutout shapes, circles, rectangles, triangles, with features down to about 5 millimeters. Here's the clever part. Instead of doing a careful grid-based raster scan, they let the robot follow a random 2D trajectory across the scanning plane. The system then measures reflections along that random path, uses an OFDM-based compressed sensing algorithm to reconstruct the image. The reconstruction combines a model of the reflection channel for each OFDM subcarrier, a spherical wave decomposition approximation, a compressed sensing solver, AMP-like, with an Onsager correction term, and total variation, minimization to exploit spatial sparsity in image gradients. In plain language, it takes fewer, smarter measurements and then lets math reconstruct the full image. The result, only about 16% of the grid points are actually sample. The system resolves 5mm features. The structural similarity index, SSIM, is around 0.88, and the full imaging process runs in about 10 seconds. Meanwhile, a separate receiver still uses the same signal for data communication. That's the essence of THz-ISAC in action. Let's connect this to real life. For autonomous vehicles, a module like this could maintain a high-capacity 220 GHz link to roadside units, edge servers, or other cars. At the same time, perform non-destructive sensing of road surfaces, tires, or nearby objects, even through some coverings. Imagine cars sharing raw LiDAR-like or camera-like data in real time at tens of gigabits per second, with terahertz beams that also help sense obstacles and infrastructure. For industrial automation and robotics, a robotic arm in a factory could use THz-ISAC for both control link plus quality inspection. It could scan inside cardboard boxes, check the porosity of materials, or inspect hidden defects, while streaming data back to an edge AI system. For 6G networks in general, this prototype is a strong sign that terahertz isn't just about faster links. It's about networks that are inherently sensing aware. Shared hardware and shared waveforms can keep costs and complexity manageable. And integrated beam tracking plus compressed sensing can make these systems usable in real, dynamic environments. Of course, there are still big challenges: power efficiency and thermal management at these frequencies, packaging and cost for mass-market automotive or industrial deployment, channel behavior outdoors in rain, fog, and complex multipath, regulations and standardized bands above 200 GHz. But as a systems demo, this 220 GHz device is a big milestone: 64 Gbps, 38 meters plus 30 degrees, millimeter resolution imaging, one box. If you work in wireless, autonomy, or industrial automation, this is a glimpse of where your network stack might be headed. Not just pushing bits, but sensing, interpreting, and reacting with the same physical layer. If you found this breakdown useful, hit like, subscribe, and share it with someone who still thinks 6G is just faster 5G. Check the description for the original Nature Communications paper and our full blog article on Newswade, where we dive into more details and references.